Hey, Sean's here, and I wanted to do something a little bit different today. I've been learning about bit shifting and like bit manipulation and stuff, just like how to more easily manage binary and like implement it in like the different programs I've been doing. And it really made me think kind of how when I was like first learning programming, like I saw like all the binary stuff and like I kind of did all the work, but like I never did put a whole lot of thought into like actually really learning it, right? Because it was kind of a pain to learn. It wasn't easy at all in terms of like digesting it, and the like literature that was there and like the teachers I had like didn't bother to make it like very easily digestible, right? They just like taught it so that you could do the tests, pass and move on, right? But I think that's a mistake. I think that, you know, binary is kind of at the core of computing. It really is computing when you think about it. So being able to do binary just makes you a better programmer, just straight up. It does. So I've thought about how to make this like the most digestible way possible, and I think really just kind of breaking down the barrier that we have mentally between numbers is like the best way to do it. So let's start off by looking at base 10. Decimal system, our system, right? So we have a number, right, in base 10. This is 1. This means 1. This always means 1. When we look at this, you know, we don't have to do any like mental computation or translation, right? We see 1, we know this means like 1 dog. You know, it means like $1, means like 1 instance of something, right? We know that we have 1 of something. So what's 2? When we see 2, we know that there's just 2 ones, right? And then that continues on as we go up. 3, 4, 5, 6, 7, 8, 9, right? And what happens when we get to 9, right? Well, we know that there's not like a single digit that represents the value 10, right? We just have to get rid of this place. This place gets set back to 0, and we put a 1 here. And that represents 10 to us. So let me ask you this. When you see this, right, this is just one number to you, right? You see this, and then you see 11, right? These are 2 different numbers. When you like mentally go between these, you see these as 2 different things. Even though 10, technically, there's 2 fields. So this is actually not a singular number. This is the value 10. When you look at it, it's 0 times 10 to the 0 equals 0, and 1 times 10 to the 1 equals, you know, 10. Sorry, it's not 1. So this is actually the composite of 2 entirely separate values. This is not just one number. Or rather, this is one number, but this is several numerals, you should say. So why is it then? Let's look at, this should be 10. Yeah, this should be 10. So this is 10 and base 2, this is 10 and base 10, right? But when you see this, you don't see this. You see a composite of values, right? To obtain the value of this, you have to mentally count, or you have to do some mental function in your head to translate the value of this, right? Typically we would of course go, you know, 0 times 2 to the 0 equals 0. 1 times 2 to the 1 equals 2. 0, there's nothing there, so we'll just do that. And then 1 times 2 to the 3 equals 8, right? So 8 plus 2 equals 10. You have to do all of that to know that this equals 10. Even though, functionally, if you had someone who was raised all their life to count in base 2 and like thought of things this way, this to them intrinsically would represent the same thing, right? Like they would see this and they would just know. So why do we have to do all this mental computation and everything? Well, like I said, it's just that mental barrier there that I'm trying to break down for you. So you want to not think of things as this. You want to think of things as this, right? You want to see each individual place, each individual field. And that, once you start doing that, like really helps you like transition between binary decimal, binary and hex, hexadecimal, ternary, centenary, so on and so forth, right? Just understanding that single principle can help you translate between a lot of different systems and fields. So, you know, let's apply that. So we have this, right, in base 2. And then, of course, when we look at this, right, you know, when you look at this, you have to do the computation in your head. You have to know that this is 8, this is 1, this is 9, and 10, right? So let's apply that. Let's apply that a little bit more broadly, right? Let's think of bit shifting, right? This is a bit more advanced thing, but let's take the number 13. This is equals 13 in base 10, right? What if we shifted the bits here? Again, bit, in this case, is just each individual digit. What if we shifted this over one spot, right? So we have this, right? We shift everything over by 1. So that means we go here, here, this is off, this is on, this is off. What does this equal when you look at this? And you see it, well, let's do the mental computation. 0, 0, 0, 1. This is in the 4th bit, so 1 times 2 to the 4th, 16, plus 8, 24, plus 2, 26. That's interesting, right? You'll notice 13, 26, what's the relationship between that? Well, 26 is just 13 times 2. So this is a multiple of 13 by a factor of 2. So when you think about it, what happened when we shifted the bit over by 1? When we went up a place, right? Well, let's think about it. We went up a place, up a digit. We know that each digit is a cycle of 2. So going up a digit is just going up by a factor of 2. It's equal to multiplying that number by 2. Does that hold true in other systems? Let's see. What's 10? If we wanted to shift the bit, so to speak, at base 10, what would we have to do? Well, again, it's a base 10 system, so we just multiply by 10. So 10 times 10 equals 100. Huh. This is a whole separate place, a whole extra field in the total numeral, the total representation of the value. So yeah, it does kind of hold true. So bit shifting in that sense is simply, again, just going up or down, you know, just decrementing it by that factor of 2, by which is, you know, the whole idea behind the base 2 system. So like if we shifted the bit down, right, we had 0, 1, 0. We wanted to shift the bit down by 1, which is, you know, most languages just do this, right? We wanted to shift the bit, you know, back this way towards the least significant bit by 1, right? That we know it's that, right? Because, you know, the final bit here, or rather, let me see, 1, 0, actually it should be that, right? So we just shift this bit down 1. So what is this doing, right? What's actually happening here without me doing this? Just think about it for a second. Pause it if you need to. Okay, so let's just start off by saying, what's this value? Well, 8 plus 2, this is 10. So we know this is 10. What's this value? This is 4 plus 1, 5. So we have 10 and 5. So when we went down a bit, and again, when we shifted the bit to the left, when we went up a bit, it was times 2. So going down a bit naturally is just dividing it by 2. This is 10. This is 5. 10 divided by 2 should be 5, right? That makes sense, because if 10 divided by 5, then we get 2. So really, this is kind of how you should be approaching every number system. Honestly, this is like the way that we were raised to think about numbers is not the mathematically correct way, which is the easiest way. And when you stop thinking of this as being a whole singular representation, a whole single constant, and just a composite of values, that's when That's when this starts getting way easier to digest, right? Because then you start just thinking, okay, well, what is this? Right, and base 10. What exactly is this? This is not 284 things. This is 200 things, 80 things, and 4 things, right? In the way that we count things, right? You would count 280 things. You could have, like, when you think about it in terms of like parallelism, right? You could have someone counting for 200 things. You could have someone counting for 80 things. You could have someone counting for 4 things, right? Different functions per bit, and that's really kind of also a lot of the idea behind like bit flags and like bit masking, things like that. It's that each individual bit has a different representation, different function that it does, and a different, you know, again, it's really just abandoning this for this. And then, you know, if we think of this, if we're thinking of numbers like this, it's very easy to transition to an entirely new system of ideas, right? Let's take ternary. I've never worked with ternary, like in my life, never done anything with it, but let's just, you know, for the sake of this, let's go to ternary. So we know that ternary is base 3. So every time we get to the number 3, then we go up a place, right? Up a field, up a digit, whatever you want to say. So let's test that idea. So 0 times, sorry, 3 to the 0 should be 0, 0, or 1 times 3 to the 0 should be 1, 2 times 3 to the 0 should be 2. Checks out. What happens when we get to 3? Do we write this? No. We write this because we've gone up a place. Now the best way to represent that is to set this digit back to 0, and then we represent this. And then now, of course, again, this is a composite of values. So we can check this out by just doing 3 to the 1. Should be 3. 0 times 3 to the 0 should be 0. 3 plus 0 equals 3. So yeah, 10 in base, 10 in base 3 or ternary should represent the value 3. And same thing, you know, as we count. Let's do 11 in base 3. Well, what should this be? This should be 4. Base 10. 12 in base 3 should be 5 in base 10. And then, of course, when we get to 12, how do we increment? Well, if we don't, we'll go to 13. We go to 20. And base 3, this represents 6 and base 10. And then it goes, follows 21. And base 3 would be 7 and base 10. 22 and base 3 be 8 and base 10. And then what happens when we get to here? Well, we're going up a place because these are both filled now. So now we go to 100. And base 3 equals 9 and base 10. And of course, we can always fact check this, knowing the way that we've been looking at binary and decimal, right? We just do 0, 3 to the 0, 0 times 3 to the 1, and 1 times 3 to the 2. Should be 1 times 9, so we know this is 9. And you can extrapolate that. Let's look at, I think it's centenary. 0, 1, 2, 3, and then at 4, we go up a place, right? So 0 would be, I mean, you know the drill now. By now, this would all check out to be right. And then this would be in base 4. What does this represent? This represents 4 in base 10. How do we represent 5? How do we represent 6? How do we represent 7? How do we represent 8? We know we would just do 2 in base 4. And that would be 8 in base 10. And again, how do we fact check this? 2 times 4 to the 1 equals 8. 0 times 4 to the 0 equals 0. And so I know that this started about being about bits and being about binary, but I really just wanted to make you understand that really it's all the same thing. It's all about just looking at a number and not seeing Again, avoid looking at numbers and seeing this, see the individual component of the total numeral that's there. Look for the summation of all those values, and then that is essentially and ultimately what you are looking at. It's not this, it's this. So, hope that helped. If it did, cool. Again, I think this is all pretty interesting, so I kind of went maybe a little bit more in depth, and might have made it a little bit more difficult to understand, but, you know, if you have any questions, drop them down below. Like, comment, subscribe, all that jazz. See you next time. Peace.